It is often heard from factory people and even consultants that real manufacturing facilities have many moving or wandering bottlenecks. Therefore, the theory of constraints is unlikely to be applicable. They usually attribute this to the change in structure of demand, the variability of processes, and other reasons. In fact, the root cause of this phenomenon is poor management. But here I'm going to talk on the definitions only. Actually, about 15 years ago, there was a thorough discussion on this issue in the TOC community. And now the following definitions can be found in the EPICS dictionary. Bottleneck is a resource whose capacity is less than the demand placed upon it, while capacity constraint is a resource that prevents a system from achieving a higher level of performance. It would seem that this is about the same thing. In order to clarify and feel the difference, let's look at the simplest case without variability and with only one type of product being manufactured that can be easily replicated without computer simulation. Consider a production line of 3 sequential processing steps producing same parts from blanks. Assume that it takes exactly 15 minutes for each part on A, then exactly 30 minutes on B, and finally exactly 60 minutes on C. Obviously, C is the only capacity constraint of this line, and maximum throughput rate of the whole system is 1 unit per hour. This is determined by the system logistics structure. But what about bottlenecks? Where and how many of these are there? It depends on how the system is managed. Suppose that we introduce one blank into the system every 60 minutes and there is one raw part before step C at the very beginning. Let's see what happens if we check the system status every 15 minutes for 8 hours. In 8 hours, there are 8 parts at the output and 1 in process right before step C. There has never been more than 1 blank in the processing queues. All resources have successfully coped with the demand placed on them. In other words, with only one capacity constraint, there were no bottlenecks in the system. C was 100% loaded, while B was only half utilized. But we can easily make it work more effectively. Let's now introduce blanks into the system every 30 minutes. As a result, we have the same 8 parts at the output and 9 more in process, including 8 before the resource C, our capacity constraint. Moreover, the queue before C is gradually growing. That is, the demand placed on this resource exceeds its capacity now. In other words, with one capacity constraint, one bottleneck appears in the system. Resource B is 100% loaded, while A is only half utilized. But it's also easily fixable. If we start introducing one blank into the system every 15 minutes, in 8 hours we will get the following. The same 8 parts at the output and 25 in the process, including 8 before step C and now 16 before B. The queue in front of B is growing, that is, the demand for this resource also exceeds its capacity. In other words, with one capacity constraint, we now have 2 bottlenecks in the system, but the load on each resource is 100%. What could be better? Note also that the queue in front of resource B is growing twice as fast as in front of C. So one might get the impression that B is capacity constraint of the whole system. Actually, we can move even further in this direction. If we introduce blanks into the system at a rate exceeding 1 unit in 15 minutes, then all 3 resources will evidently become bottlenecks. Well, Summing up all the above, let's formulate the following takeaways. With a given demand and product mix structure, there is usually only one capacity constraint in the system. With only one capacity constraint, the number of bottlenecks, 0, 1 or more, and their locations depend on how this production system is managed. Generally speaking, it is incorrect to identify the resource with the longest queue in front as the system's capacity constraint. Capacity constraints as control points for the entire system are good, while bottlenecks, slowing down flows, are bad.